Hi, I'm Dr. Gareth Moore from RP Photonics, and welcome to this RP Fiber Power tutorial series. Today I'm going to show you how simple to use, yet powerful, our fiber simulation software is. Let's dive right in with a case study which you can find on our website. Here we want to design a passive germanosilicate fiber, suitable for propagating a single mode signal at around 1550 nanometers in the Telecom C-band. Our goal is a fiber with relatively flat dispersion around that 1550 nanometers and an effective mode area of 80 square microns. We'll first try to simulate the common Corning's SMF28 fiber to understand its properties, and then we'll move on to modifying the doping profile of the fiber in a number of different ways to try reach our goal. Let's see how this is done with RP Fiber Power. For this simulation, we use the power form titled Modes of a Germanosilicate Fiber. We begin with the simplest kind of refractive index, the step index fiber. These have a constant refractive index within the fiber core. We'll try and analyze a Corning's SMF28, a widely used standard single mode fiber in telecommunications. We start by entering the core diameter of 8.2 micrometers and a germanium dioxide concentration of 4.5%, which gives us a numerical aperture of 0.14. The cladding concentration is set to 0% and we choose a wavelength of 1550 nanometers. We confirm the numerical aperture of 0.14 and observe a V number below 2.4, which means the fiber supports only the LP01 mode as expected. However, we notice that the effective mode area is calculated to be just 64.4 square microns, whereas Corning's specifies the effective mode area of approximately 87 square micrometers at 1550 nanometers. So, we reduce the germanium dioxide concentration in the core to 3.5%. This adjustment results in a numerical aperture of 0.123 and an effective mode area of 76 square microns. Still a bit low, but closer to our target. We can now generate a diagram to observe how the dispersion changes with different wavelengths. In the telecom context, we'll use the units of picoseconds per nanometer per kilometer. Looking at a broader range, we identify the LP11 mode cutoff wavelength at 1314 nanometers, aligning well with Corning specifications. Zooming in, we see the dispersion increase significantly at longer wavelengths, becoming quite anomalous around the 1.5 micron region. Now, let's explore modifications to bring the dispersion closer to zero at 1550 nanometers. We start by reducing the core diameter from 8.2 to 4 microns and increase the germanium dioxide concentration to 14.7% to maintain a V number of 2.05. This change shifts the zero dispersion wavelength to 1565 nanometers. However, small core diameters present challenges. The effective mode area drops significantly to 18.2 square microns, making splicing to standard single mode fibers pretty lossy. Additionally, the higher refractive index contrast increases propagation losses due to stronger scattering at irregularities. Plus, there is still a notable slope in the dispersion curve, which is not ideal. We can attempt to improve the effective mode area by reducing the germanium dioxide concentration to 10%. This adjustment increases the effective mode area to 25.4 square microns, but shifts the zero dispersion wavelength to 1668 nanometers. By slightly increasing the core diameter to 4.28 microns, we shift the zero dispersion back to 1564 nanometers while maintaining a larger, though still insufficient, effective mode area of around 25 square microns, with a reasonable V number of 1.18. This demonstrates how sensitive fiber properties are to these changes. It's clear that this step index profile probably won't achieve a flat dispersion curve. To achieve that, we'll need to explore some more complex doping profiles. One option is to use a triangular doping profile. In the software, we simply enter an expression that varies with the core's radius, starting at the concentration, C0, and decreasing as R approaches the core radius. We define C0 as 8% in the additional definition section for easy adjustment, and set the core diameter to 5 microns. These parameters already perform reasonably well, giving us a zero dispersion wavelength at 1559 nanometers and a substantial effective mode area of 106 square microns. Since we'll be adjusting these parameters frequently, let's add some additional code to quickly print out the zero dispersion wavelength and the corresponding effective mode area. If this feels overwhelming, remember our software is thoroughly documented and technical support is never far away. Now, as we try different parameters, we can see the key results straight away. But how do we know if we're actually getting closer to our goal? This is where we can define a figure of merit function that gives us a number to how good our parameter set is. We define our desired final zero dispersion wavelength as 1550 nanometers and effective mode area as 80 square microns. We then take the difference between our calculated and desired values, normalize so that there's a result of 1 for every 10 nanometer deviation in the zero dispersion wavelength and 10 square micron effective mode area. Now we can think of these two values as a measure of how far we are from our goal, but they are in different directions. So in the same way as finding the length of a vector with different components, we take the square root of the sum of the squares, leaving us with one unitless number that quantifies how close we are to our goal. Printing this number for different parameter sets gives us an idea of how this works, where the lower the number, the better the parameter set is. We can now take this a step further by using the software to automatically find the optimal core radius and maximum germanium dioxide concentration. Using the vary command, we can vary the core radius between 2 and 10 microns and the starting concentration between 0 and 20%, aiming to minimize the figure of merit. For a core diameter of 5.66 microns and a doping concentration of 7.6%, we achieve an extremely low figure of merit. Let's input these values and review the results. We obtain an effective mode area of 80.5 square micrometers, with a zero dispersion wavelength of 1550 nanometers. However, the mode field extends significantly into the cladding, which could reduce the robustness of the LP01 guidance and increase the sensitivity to microbending losses. Additionally, the dispersion profile still shows a substantial wavelength dependent slope, so let's explore another doping profile to improve this. Lastly, we turn to a dispersion flattened fiber with a W-shaped doping profile. To achieve this, we define a profile where the core has a doping concentration C1 from the center to some radius R1, followed by zero doping up to the core radius, and a higher germanium dioxide concentration in the cladding. This gives us a curved dispersion profile and a somewhat W-shaped refractive index profile. This also gives us 4 parameters to optimize: the core doping concentration, the inner ring radius, the core radius, and the cladding concentration. We set up a figure of merit function as before, but now we optimize for a flat dispersion profile around 1550 nanometers and an effective mode area of 80 square microns. We again use the vary function to optimize all 4 parameters. With the optimized values, we achieve a satisfying dispersion profile, which is relatively flat around 1550 nanometers, and a mode size that is well confined to the core, ensuring robust guiding. However, we fall short of our effective mode area goal. This suggests that a flat dispersion profile with this doping pattern is only really feasible with an impractically small core. We've seen how quick and easy it is to run through multiple design iterations of the fiber. We've also seen how useful numerical optimization can be for finding the right parameters for your design. Imagine doing this with trial and error in the lab. But most importantly, we've seen how simulation software like RP Fiber Power is not only useful, but essential for designing such complex fibers. In the end, we come out not only with a great design, but a deeper understanding of our system. To learn more about what our software can do for you, visit our website and click on the Software tab. For more case studies like these, click on the Case Studies and Tutorial button under the Encyclopedia tab. Thanks for watching, and please feel free to reach out with any questions.